All right, so let's put all this together and what we did in the last lecture. And in this module, let's go through an example, an X-ray diffraction example, using all that we've just talked about in the previous lecture. All right, so this is the question that I have for you. This will be on your quiz, so you can go ahead after the intro here and pause it, try to work that out yourself, answer the question, and come back and we'll work it together. So I've given you a pattern below here, and what I want you to do is all the peaks are already labeled. So what I want you to do is see if you can identify whether it's simple cubic, BCC, or FCC, what type of cubic system it is. Once you know that, take a look at the first peak, excuse me, and I've given you the angle for it, so you don't have to try to guess what it is. So that first peak is at 31.26 degrees. So based on what you know from the first question and the angle given to you and the fact that it's the 111 plane, and then also you're given the radiation, so copper K alpha, and I tell you that this is the wavelength of 0.154 nanometers. What I want you to do is put all that together and calculate the lattice parameter. So it's going to kind of take everything that we just talked about in the previous lecture and modules, kind of putting that all together to determine what the lattice parameter is. So see if you can calculate that lattice parameter with all that information, and then we'll come back and we will work through this example. All right, so let's take a look at this problem. So the first thing I want to do is the first questions, excuse me, the first question it's asking is, what type of cubic system is it? And so we just finished in the previous module talking about those extinction rules. And so if we are given the HKL values for the first, second, third, fourth, fifth, sixth, seventh, so on, we can determine this by those extinction or reflection rules. So we've got a 111 and then a 200 and a 220. Those are our first three. So let's go back to the table. You can also find this in your book and see if we can find something that matches those values. All right, so here's our reflection rules, right? 200, 111, let's look for that, the first peak. So again, simple cubic, FCC, BCC. If it is one of these, it should have the first peak being 111, right? And if we look at these, the only one with the first reflection of 111 is FCC, right? The first value here. And sure enough, if we look at those reflections present, they should either be all odd or all even. And so let's go back. So 111, all of those are odd. All of those indices are 1, 1, 1. Those are all odd. 2s and 0s, that's all even. 2s and 0s, all even. 3s and 1s, odd. 2s, even. And so this is FCC based on those extinction rules. All right, so we know it's FCC. So that's important. We want to make sure that we know it's FCC. So now let's go ahead and look at the second part of that expression. And for that, I'm going to move over to a piece of paper to help us out with that. All right, so in the previous part, we saw that we identified as FCC from the peaks available, right? All reflections were either all odd or all even. So all of those values. So let's go to the part about calculating the lattice parameter. And let's just rewrite what we know. So we know that first peak that has two theta value of 31.26 degrees. We also know that that was the 111 plane, right? It was labeled as such. All right. We also used copper K alpha radiation, which we saw had a wavelength, so lambda, of 0.154 nanometers. And what we want to calculate is the lattice parameter, A, since it's cubic, we want to calculate this. All right, so we've got the wavelength, we've got the angle measurement, and so the first thing we're going to do is recall Bragg's law. N lambda equals 2 DHKL sine theta, right? That's Bragg's law. So if we know the radiation, if we know the angle, we can determine the distance between those planes, DHKL. So if I solve for that, this will be n lambda over 2 sine theta. I just rearranged this expression. We know n equals 1, right? First order reflections. And so what we want to plug in here then is the wavelength. So 1 times 0.154 nanometers. And then on the bottom, we've got 2 sine theta. So 2 sine, but the angle over here was actually 2 theta. So we actually have to divide that by 2, right? So when you're calculating this, so 1 times, and I apologize for the slop here, but 1 times 0.154 nanometers divided by 2 times sine of the angle, make sure that you keep track of the units. So this is in degrees right now, so make sure your calculator is set up to do that. And once you calculate that, what you find is that the DHKL value, and you can plug in, and you can call this the 111, but this value is equal to 0.2858 nanometers. So this is the spacing between these 111 type planes in the material that we're dealing with. So that's the first part. So we know that, but it's actually asking for A, right? We just have D right now. Okay, so that brings us to our second expression. From a previous slide, we saw that for the cubic system, we had an expression that DHKL equaled the lattice parameter over the square root of h squared plus k squared plus L squared, right? That was an expression we saw earlier. So if we want to solve for A, we can multiply this term by DHKL, which we just calculated. And that will give us A. So again, the peak was labeled as 111, so we know this is 1, the h is 1 squared, plus k is 1, and then L is also 1. And then multiply by this term. That will give us A. So basically here, this is going to give us 1 plus 1 plus 1. So we have square root of 3 times our D spacing gives us our lattice parameter. And that value, when you calculate this, is 0.4950 nanometers as the value of A. So we had to kind of do multiple things, right? We had to look at the pattern, to look at the extinction rules to determine FCC. And then we could calculate the D spacing from the angle. And then using that, we can get the lattice parameter, knowing what the plane is and knowing the D spacing, we can get A. So that's what we've done here. And so I'm going to switch it back to the slides to show you one more thing, but this was what we were after here. All right, so we've determined that this is FCC, and we've calculated the lattice parameter of this material. And so if you're asking yourself, what was the point, right? Well, we actually determined a lot of information from this pattern, right? Because of the planes that exist, because of the peaks that exist, we're able to figure out that this was FCC. And then from our calculations where the positions of the peaks are located, we're able to determine that the lattice parameter, so the size of the unit cell, is 0.4950. So the power of this is that we can go through and compare that to known materials, right? And if we look at, if let's say this is an element, if we compare this to the list of lattice parameters for elements, what we find is that the lattice parameter and the FCC of different FCC metals show that this is lead. Lead has a lattice parameter of 0.4920, so very close to what we calculated. And lead is an FCC type of element. So by being able to calculate and determine what the structure is, we can, or by knowing the lattice parameter, we can then determine what the crystal structure is. So this is kind of a an intro example, and that's really all I want you to be able to determine here. But as you go into, if you ever go into more depth on X-ray diffraction, and we do this in other courses in MSE, you'll find that we can actually determine from a pattern what we have, what crystal structure we have, what lattice parameter, and potentially what element or compound that we have as an example.